I want to talk about another application of the double integral, and that is calculating surface area. So the idea is this: I've got my XYZ system here. I've got a region down here in the plane. I'll call it D. For each point in that region, I have a function defined. So I'm going to draw, actually in red here, I'll draw the surface up above. So there's some surface here. Z is some function of x and y. And the idea is I want to calculate above the region D on that surface, whatever this looks like here on the surface up above, I want to calculate how much area there is. Now it's not going to be the same as D because D is flat and the surface is bent. So there's probably going to be more area up above. I can't imagine how there would be less when you bend it here. But if I had to get some paint this and figure out how much paint I need to know the surface area. Okay. And the way we're going to do this is we're going to cut the region D up into a bunch of little pieces, which actually then cuts the region up here into a bunch of little pieces. Right? A lot of rectangles down there kind of turn into maybe parallelograms up there. And what I want to do is essentially calculate the area of each little piece and then add up all those little pieces. Well, that would be an integral, right? So let's look at one individual rectangle and what happens, right? So down in the XY plane, I've got a rectangle. And up above, that corresponds to some surface. So right up above each one of them, straight up and down here. So there's some surface up there. What I'm going to do is I'm essentially going to approximate this surface with a parallelogram. So I'm going to take a line that's tangent to the curve there. I'm going to take a tangent plane. I'm going to take a tangent there and end up drawing a plane, a little piece of a plane. Right? Well, the question is, how do you find the tangent line at in this direction and in that direction? Well, we're talking partial derivatives here. So if this is the x direction down here and that's the y direction, then I can look at sort of vector parallel here by looking at some distance in the x direction. So let's call this vector here Vx. So Vx is going to be, I'm going to have a little bit of displacement in the x direction, nothing in the y direction, and then I have to figure out how far up to go in the z direction. Well, that's going to be essentially the slope times how far I move in the x direction. Well, the slope is calculated by partial derivative, right? This is Calc 3 stuff now. So if I look at essentially the partial derivative with respect to x, I'll notate it this way, then times delta x. That's going to be a vector that has this for an x component, 0 for a y component, and the slope times delta x, so the appropriate amount here to be pointing in the direction that I want. Likewise, if I look at this vector over here, Vy, so this little vector in the y direction, so 0 in the x direction, move over some delta y down here, whatever that delta y is, that's this direction here, and then how far up or down do I need to go? Well, that's going to be the derivative in the y direction, so the partial of f with respect to y, times the amount that you move in the y direction. Okay. Now, to find the area of a parallelogram, this is, how much linear algebra do you know here from Calc 3? What did we learn here? If I've got two vectors, I'm just going to call them u and v for now. They determine a parallelogram, and it turns out that the area of that parallelogram is the length of the cross product of the two vectors. Okay, so the area of this red parallelogram up here, which I'm going to call a little dA, well, maybe not dA. dA is down here. Let's say ds, d surface area. Okay, so actually maybe it's easier if I say delta s, some sort of big change in surface area, is the length of the cross product of these two things here. So I've got delta x, comma 0, comma the gradient times delta x, crossed with this other vector. And I'm going to need more room, so let me circle this and move it over. Right. 0 delta y, the partial with respect to y times delta y. Okay. So to do that cross product, the way I do cross products is to do it as a determinant of vector. So I've got I, j, k. The first one here, delta x, 0, partial of f with respect to x times delta x, and 0 delta y, and the partial with respect to y times delta y. Right? And so I'm taking the length of this cross product, right? So the inside absolute values is actually a determinant, and the outside absolute values is the length of the vector here. So so what do I have? The first component is I times that, so I've got negative the gradient of y. It's not the gradient of y, sorry. The delta y times partial with respect to x times delta x. Okay, and then minus. So this one is now this minus that, and so that actually becomes, I do it backwards, this minus that. So this is minus delta x times fy times delta y. And lastly, I've got this times that, so that's just delta x times delta y. And then I need the length of that vector. Okay, here we go. Let's see. So I've got the square root of, actually before I do that, I'm going to notice that I've got a factor of delta x times delta y in each of the components here. So I'm just going to rewrite this way, minus the partial of f with respect to x, minus the partial of f with respect to y, comma 1. Actually, if you remember anything about Calc 3, this vector right here is a normal vector to the tangent plane. So, which it should be, because we're taking the cross product of two tangent vectors, and so that other one should be perpendicular to both of those, and the length of that is the area of that parallelogram. So here we go. This is delta x delta y times the square root of fx squared plus fy squared plus 1. I want to point out a similarity here, that when we did arc length back in Calc 2, when we had, from A to B here, we took it and we cut it up into a bunch of little pieces. We had that the arc length was the integral of the square root of 1 plus dy dx times dx. Well, that's essentially what we have here. 1 plus the derivative squared. Oh, sorry, that was actually squared. And this one now just has that extra variable in it, and a dA instead of a delta x delta y. So what we've got here now is that the surface area is the double integral of the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared times dA, and you integrate over the region. Right? Very much like the arc length formula, but now this is the surface area, and we've got an extra variable involved here. So this is the surface area when you have the surface described as a function of x and y. I'm going to stop this video here and do an example in the next one.